In 1903, a woman walked into a room full of men who believed she had no right to be there. She carried with her a discovery so dangerous it would eventually kill her, yet so revolutionary it would reshape the 20th century. Her hands were scarred from radiation burns she didn't yet understand. Her notebooks, even today, are too radioactive to touch without protection. Marie Curie didn't just break barriers. She shattered them so completely that the pieces could never be reassembled. But before the Nobel Prizes, before the fame, before her name became synonymous with scientific genius, there was a girl in Russian-occupied Poland who wasn't allowed to attend university simply because she was born female. This is the story of how she went from smuggling banned books in Warsaw to handling substances that glowed in the dark, from sleeping in an unheated Paris garret to standing before the King of Sweden, from being dismissed as a mere assistant to becoming the only person ever to win Nobel Prizes in 2 different sciences. What drove someone to spend years stirring boiling vats of radioactive material with an iron rod nearly as tall as herself? What kind of obsession makes you ignore blistered hands, chronic illness, and a scientific establishment that wanted nothing more than to see you fail? The answer begins in a city that officially didn't exist. Warsaw in 1867 was a ghost, not literally, but politically. After the failed uprising of 1863, the Russian Empire had erased Poland from the map so thoroughly that speaking Polish in schools was forbidden, teaching Polish history was criminal, and dreams of independence could land you in Siberia. Into this suffocating atmosphere of occupation and oppression, on November 7th, Maria Salomea Sklodowska entered the world. Her father, Władysław Sklodowski, taught mathematics and physics at a gymnasium. Her mother, Bronislawa, had been a respected educator before tuberculosis began its slow theft of her strength. They had 5 children, and Maria was the youngest, a detail that would prove both burden and liberation. The apartment where she grew up was filled with scientific instruments, glass beakers, a small laboratory that her father maintained despite the Russians confiscating most of his equipment as punishment for suspected revolutionary sympathies. Young Maria would watch him demonstrate physics principles, her grey eyes absorbing everything. She learned to read at 4. By 5, she was correcting her older siblings' homework. But childhood in occupied Warsaw wasn't measured in birthday parties and carefree play. It was measured in loss. When Maria was 8, her oldest sister, Zofia, contracted typhus and died. The girl who had been full of life one week was gone the next, and Maria learned that the world could take away what you loved without warning or mercy. 2 years later, tuberculosis finally claimed her mother. Bronislawa had kept her distance from her children for years, afraid of infecting them, and so Maria lost her mother twice, first to fear and caution, then to death. These weren't just personal tragedies, they were formative wounds that shaped everything Maria would become. She developed what her siblings called an unusual gravity, a seriousness that sat oddly on such young shoulders. She threw herself into books the way other children threw themselves into games, finding in mathematics and literature a refuge from grief. The Russian authorities had different plans for Polish girls. Education was meant to produce obedient wives and mothers, not independent thinkers. But Maria's father, despite his own precarious position, couldn't bear to see his brilliant daughter's mind wasted. He tutored her secretly, passing along not just knowledge, but something more dangerous, the belief that she had the right to think for herself. At 15, Maria graduated from gymnasium with a gold medal, the top student in her class. The achievement was bittersweet. Russian universities didn't admit women. Polish universities didn't exist. For young men, the path forward was clear. Study abroad, build a career, return to help liberate Poland. For young women, the path simply ended, or it was supposed to. What Maria discovered was an underground network that would change her life. The Flying University, they called it, a secret institution that moved from apartment to apartment, teaching what the Russians had banned: Polish history, Polish literature, real science instead of the watered-down curriculum the occupiers permitted. It was illegal, dangerous, and absolutely necessary. For 2 years, Maria attended these clandestine lectures, learning from professors who risked imprisonment to teach. She absorbed chemistry, anatomy, natural history, all the subjects that fascinated her, all the knowledge that official institutions denied her. But it wasn't enough. She wanted more than hidden lectures in changing locations. She wanted a real education, a real laboratory, a real chance. The problem was money. Her father's position paid barely enough to support himself. The family had been sliding toward poverty for years. Maria took a job as a governess, moving to the countryside to live with a wealthy family and tutor their children. The pay was minimal, the work tedious, but she saved every kopeck she could. It was during this period that Maria made a pact with her older sister, Bronislawa. Bronia wanted to study medicine in Paris, but faced the same financial impossibility. They struck a deal. Maria would work as a governess for several years, sending her savings to support Bronia through medical school. Once Bronia graduated and established herself, she would send for Maria and support her in turn. It was a plan that required extraordinary patience and faith. Maria was 18 when she began this arrangement. She would be 24 before she finally escaped. Those 6 years in the countryside were not wasted. Between tutoring sessions, Maria continued her self-education, reading every scientific text she could acquire, conducting small experiments in her spare time. She also fell in love, briefly and disastrously, with the oldest son of the family she worked for. His parents forbade the relationship, their son too important to marry a governess, and Maria learned another lesson about the world's opinion of women without money or position. The rejection stung, but it also hardened something in her. She would not spend her life waiting for permission from people who thought her worthless. She would earn her own position, her own reputation, her own life. In 1891, the letter finally arrived. Bronia had married a Polish physician, established a medical practice, and now had a spare room in Paris. It was time. Maria packed her few possessions, said goodbye to her father, and boarded a 4th-class train for the 30-hour journey to France. She was 24 years old, spoke almost no French, and carried everything she owned in a single trunk. She had no idea she was about to walk into a discovery that would redefine reality itself. Paris in the 1890s was the undisputed capital of science. The Sorbonne attracted brilliant minds from across Europe. Its laboratories were equipped with instruments that Maria had only read about in books. And crucially, unlike every institution in Poland or Russia, it admitted women. Not that it welcomed them. Women at the Sorbonne in 1891 were rare enough to draw stares, whispers, sometimes outright hostility. The few who attempted scientific study were assumed to be dilettantes, playing at scholarship until marriage called them to their real duties. Marie, as she now called herself, adopting the French version of her name, cared nothing for these assumptions. She enrolled in the Faculty of Sciences, focusing on physics and mathematics. Her French was still rough, her background education was uneven, full of gaps from her makeshift Polish schooling, but her determination was absolute. While other students socialized, attended parties, enjoyed the pleasures of Paris, Marie lived like a monk. The spare room in Bronia's apartment was comfortable, but it was also in a distant neighborhood, requiring a long commute to the university. More importantly, it was full of people: Bronia's husband, their friends, the social obligations that ate into study time. After a few months, Marie made a decision that shocked her sister. She would move out, live alone, rent the cheapest room she could find near the Sorbonne. What she found was a 6th-floor garret in the Latin Quarter. No heat except a small stove, no gas for cooking. In winter, the water in her wash basin froze solid. She lived on bread, chocolate, and fruit, whatever she could eat without cooking, because meals took time away from study. On the coldest nights, she piled all her clothes on top of her blankets and still shivered until dawn. Her fellow students thought she was insane. Why would anyone choose such deprivation? But Marie understood something they didn't. Comfort was a luxury she couldn't afford, not in money, but in focus. Every hour spent in warmth and company was an hour not spent in the library, not spent working through physics problems, not spent catching up on the years that Russian occupation had stolen from her. She fainted once during a lecture, collapsing from a combination of cold, hunger, and exhaustion. Bronia found out, arrived furious, and dragged her sister back to the apartment, forcing food into her and warmth into her bones. Marie recovered and promptly returned to her garret. She would not be saved from her own ambition. In 1893, Marie earned her degree in physics, finishing first in her class. The girl who had arrived speaking broken French, whose prior education had been cobbled together from secret lectures and borrowed books, had outperformed every student at France's most prestigious university. The following year, she earned a second degree in mathematics, finishing second in her class. She should have been celebrating. Instead, she was calculating. 2 degrees were impressive, but they opened no doors for women in academic science. She needed something more. She needed original research, a discovery that couldn't be dismissed or attributed to male colleagues. She needed to prove not just competence but brilliance. What she didn't know was that the tools for that proof were about to literally fall into her hands. In 1894, while searching for laboratory space to conduct research on the magnetic properties of steel, Marie was introduced to Pierre Curie. He was 35, already respected in French scientific circles for his work on crystallography and magnetism. He had a laboratory, modest but functional, and a reputation for taking scientific questions seriously regardless of who asked them. Their first conversation lasted hours. Pierre was accustomed to colleagues who treated physics as a career, a respectable profession. Marie treated it as something else entirely, a calling, an obsession, the only thing that mattered. He found this fascinating. She found his laboratory indispensable. They began working together on Marie's steel research. Pierre was struck by her absolute precision, her refusal to accept results until they'd been verified repeatedly, her willingness to spend weeks on a single measurement to ensure accuracy. He proposed marriage within months. Marie refused. She had plans to return to Poland, to teach, to contribute to her country's resistance against occupation. Pierre argued that she could do more in Paris, that the laboratories and resources here far exceeded anything available in Warsaw. Marie remained unconvinced, until Pierre made her an offer that changed everything. He would move to Poland with her, if that's what she wanted. He would abandon his position, his laboratory, his entire scientific career, just to be near her. It was an absurd sacrifice, and Marie knew it, but it told her something crucial about the man making the offer. He saw her not as a wife to support his work, but as a scientist whose work mattered as much as his own. They married in July 1895, a simple civil ceremony with no church, no white dress, no religious vows. Marie wore a dark blue outfit that she could later use as a laboratory dress. They spent their honeymoon on bicycles, touring the French countryside. Then they returned to Paris and to work. Marie took Pierre's name, though she would later insist on using both, Marie Skłodowska-Curie, refusing to let her Polish identity disappear into French convention. She was now a married woman, which society assumed meant the end of her scientific ambitions. She was now 28 years old, which meant time was running out to establish herself before being dismissed as too old. She needed a research topic for her doctoral thesis. She needed something that no one else had claimed, something that would force the scientific establishment to pay attention. In November 1895, a German physicist named Wilhelm Röntgen discovered something impossible. He'd been experimenting with cathode ray tubes when he noticed that a fluorescent screen across the room began to glow, even though the tube was covered. Something was emanating from the tube, something invisible that could pass through paper, wood, even human flesh. Röntgen called them X-rays, and within weeks, the world was obsessed. Then in 1896, Henri Becquerel made an equally strange discovery. He'd been studying phosphorescence, trying to determine if materials that glowed after sun exposure also emitted X-rays. He wrapped photographic plates in black paper, placed phosphorescent uranium salts on top, and left them in sunlight. When he developed the plates, they were fogged, as if exposed to light. But then Becquerel made a mistake that became a breakthrough. He prepared another experiment, but the weather turned cloudy, so he stuck the uranium salts and wrapped plates in a drawer to wait for sun. Days later, expecting nothing, he developed the plates anyway. They were fogged even more strongly than before. The uranium was emitting something continuously, powerfully, without any external energy source. It wasn't phosphorescence. It was something entirely new, something that violated every known principle of physics. Energy couldn't come from nowhere, yet here it was, pouring out of uranium for no apparent reason. Most scientists found this interesting, but moved on to other questions. Marie Curie looked at Becquerel's uranium rays and saw her future. Marie needed a laboratory. What she got was a storage room. The School of Physics and Chemistry, where Pierre worked, offered her a ground floor space that had previously housed machines. It was damp, drafty, and so cold in winter that solutions would freeze in their containers. The ceiling leaked. There was no proper ventilation. The single stove barely heated a fraction of the room. It was perfect, because it was hers. She set up her equipment in early 1897, while 7 months pregnant with her first daughter, Irene. The pregnancy slowed her movements, but not her mind. She decided on her research question with characteristic precision. Becquerel had discovered that uranium emitted mysterious rays. But was uranium the only element that did this? And what exactly were these rays? The scientific community had moved on, distracted by X-rays and other fashionable topics. Marie saw opportunity in their neglect. She needed to measure the ray's intensity. Becquerel had used photographic plates, but that method was imprecise and slow. Marie turned instead to an instrument that Pierre and his brother Jacques had invented years earlier. The electrometer measured tiny electrical currents with extraordinary sensitivity. When radiation struck air molecules, it ionized them, creating a measurable electrical charge. By quantifying this charge, Marie could measure radiation intensity with unprecedented accuracy. She worked methodically, testing every uranium compound she could obtain. The results were consistent. The intensity of radiation depended only on the amount of uranium present, not on the compound's chemical form, not on temperature, not on whether the sample was wet or dry, solid or powdered. The rays seemed to come from the uranium atoms themselves, not from any molecular arrangement. This was strange. Chemistry dealt with how atoms combined and separated. But the uranium rays appeared to be a property of the atom itself, something fundamental and unchanging. Marie was touching the edge of something that chemistry couldn't explain. Then she tested other elements. Most showed nothing. But 2 samples made her electrometer readings jump. Thorium emitted rays just like uranium. Here was the answer to her first question. Uranium wasn't unique, but something else caught her attention. 2 uranium ores, pitch blender and chalcolite, produced readings 4 times stronger than pure uranium. That made no sense. If radiation depended only on uranium content, and these ores contained less uranium than pure uranium metal, they should produce weaker readings, not stronger ones. She tested the samples again. Same result. She checked her instruments. They were working perfectly. She analysed the chemical composition of the ores. Perhaps some unknown impurity was affecting the measurements. Pierre noticed his wife's unusual silence at dinner. Marie was never quiet, unless she was wrestling with a problem that mattered. "What is it?" he asked. "The pitch blender," she said. "The readings are wrong, or they're right, which means something else is in there, something more active than uranium." Pierre understood immediately. If the ores were more radioactive than pure uranium, they must contain an unknown element, an element that no one had ever isolated or identified, an element that was far more radioactive than anything yet discovered. The implication was extraordinary. Marie might have found not just a new phenomenon, but an entirely new element, perhaps more than one. She wrote in her notebook, "This fact is very remarkable and leads to the belief that these minerals may contain an element which is much more active than uranium." It was April 1898. Marie was 30 years old. She'd been working in her storage room laboratory for barely a year, and she'd just identified a problem that would consume the next 4 years of her life and revolutionize physics. But first she would need help, because finding an unknown element hiding in ore would require processing tons of material. It would require chemical techniques she'd have to invent. It would require a larger space, more equipment, and another pair of hands. Pierre made a decision. He abandoned his own research on crystals, work he'd been pursuing for years, to join Marie's investigation. It was a staggering sacrifice. He was an established physicist with his own laboratory and research program. She was a doctoral student working in a storage room, but Pierre had recognized something that few others had. Marie wasn't just pursuing an interesting anomaly, she was onto something fundamental. They became partners in the truest sense. Pierre handled the physics, measuring radiation and developing theories. Marie focused on the chemistry, isolating and purifying materials. Every evening, they compared notes, challenged each other's conclusions, planned the next day's work. Their first task was to prove that the unknown element actually existed. They obtained several kilograms of pitch blend and began systematic chemical separations. They dissolved the ore in acid, precipitated different fractions, tested each fraction's radioactivity, followed the radiation trail through the chemical maze. By June, they'd isolated a substance from the ore that was 150 times more radioactive than uranium. It behaved chemically like bismuth, but it wasn't bismuth. On July 18, 1898, they announced their discovery in a paper presented to the Academy of Sciences. They proposed that pitch blender contained a new element, which Marie named polonium, after her homeland. The paper was 6 paragraphs long. The final sentence read, "If the existence of this new metal is confirmed, we propose to call it polonium, after the name of the country of origin of one of us." Or, that "if" mattered. The scientific community wouldn't accept their claim without definitive proof. They needed to isolate polonium in pure form, determine its atomic weight, and identify its spectral lines. Marie and Pierre had announced a discovery they couldn't yet prove, but they weren't finished. As they continued separating pitch blender fractions, they found something else. Another substance, chemically similar to barium, that was even more radioactive than polonium. By December 1898, they were ready to announce a second new element. Marie named it radium, from the Latin word for ray. The paper announcing radium contained a sentence that would prove prophetic. "One of us has shown that radium compounds are spontaneously luminous." They had a sample of radium-enriched barium chloride. In the dark, it glowed with a pale blue light, like moonlight captured in a bottle. Pierre would carry a tube of it in his pocket, delighting in showing people the substance that glowed without any external energy source. Neither of them yet understood what that glow meant, that it was their atoms literally tearing themselves apart, releasing energy that had been locked inside matter since the universe began. That the glow was dangerous, for now it was simply beautiful. But they still hadn't isolated pure radium. They'd found traces of it, enriched it, proven it existed, yet the Academy of Sciences demanded more. They needed pure radium, enough to determine its atomic weight precisely, to study its properties definitively. Marie calculated what this would require. Radium occurred in pitch blender at roughly 1 part in a million. To obtain a single gram of pure radium, they would need to process several tons of ore. They had no money for this. A professor's salary was modest, and they had a child to support. Pierre's father, who lived with them, helped with Irene, but they couldn't afford to purchase tons of uranium ore. Marie found a solution. The uranium had already been extracted from pitch blende for industrial use. The leftover residue, considered worthless, was dumped in piles near the mines in Austria. The mining company would give it to them for free if they paid only for transportation. The Austrian government, amused by these strange French scientists who wanted their waste, agreed. In late 1898, a wagon delivered a ton of brown residue to the School of Physics. The pile sat in the courtyard, and Marie got to work. They needed a larger space. The school offered them an abandoned shed that had once been used for dissections by medical students. It had a skylight that leaked, no proper chimney, and heating that barely functioned. In summer, it was unbearably hot. In winter, brutally cold. But it had space. Marie set up huge iron cauldrons in the courtyard outside the shed. She would boil 20 kilograms of residue at a time, stirring with an iron rod nearly as tall as herself. The work was industrial, physical, exhausting. She was a chemist performing the labour of a factory worker, boiling, filtering, precipitating, over and over. Pierre focused on the final purification steps inside the shed, working with the partially refined materials that Marie produced. Their process involved dozens of crystallizations, each one concentrating the radium slightly more. The work was monotonous and physically demanding. Marie's hands became scarred and burned from the acids and the constant labour. They worked without proper safety equipment, without understanding that the materials they handled so casually were poisoning them with every breath. But slowly, painfully, over 4 years, the radium content in their samples increased. From 150 times more radioactive than uranium to 1,000 times to 10,000 times. During these years, Marie also had to defend her doctoral thesis, give birth to her second daughter Ave, manage a household, and deal with the constant financial pressure of feeding a family on one professor's salary. She cycled between the shed, her home, and the market, trying to find the cheapest cuts of meat and vegetables, while simultaneously solving the puzzle of radium chemistry. She lost weight. She was perpetually exhausted. Friends worried about her health. She kept working. Pierre's health was also declining. He developed strange pains in his bones and joints. His hands trembled. He couldn't sleep. They both attributed it to overwork and the damp, cold conditions of the shed. They never connected their symptoms to the glowing tubes Pierre carried in his pockets or the radium dust that covered their laboratory notebooks. By 1902, Marie had processed 8 tons of pitch blende residue. She'd performed thousands of crystallizations. She'd spent endless hours stirring boiling solutions in the courtyard, breathing fumes, handling materials that would later be understood as lethally dangerous. And she'd succeeded. She had isolated 1/10 of a gram of pure radium chloride. A tiny amount, but enough. Enough to determine radium's atomic weight with precision. Enough to prove beyond any doubt that radium was a genuine element. The atomic weight was 225. Radium's place in the periodic table was confirmed. Marie Curie had discovered not one, but 2 new elements, proven their existence through years of grinding physical labour, and solved the mystery of why pitch blende was more radioactive than uranium. In June 1903, she defended her doctoral thesis. The title was Research on Radioactive Substances. It described the discovery of polonium and radium, the measurement of their properties, and the development of techniques for isolating them from ore. The defense took place at the Sorbonne. The room was packed. Women weren't common in French universities, and a woman defending a physics doctorate was unprecedented. The examining committee included Henri Poincaré, one of the greatest mathematicians of the age, and Gabriel Lippmann, who would win the Nobel Prize 5 years later. Marie presented her work calmly, answering technical questions with precision. The committee was impressed not just by her discoveries, but by the rigor of her methods and the clarity of her thinking. She was awarded her doctorate with the distinction Très Honorable, the highest honour. She was 35 years old. She'd spent 8 years pursuing this work, from her first measurements in 1897 to this defence in 1903. She was the first woman in France to earn a doctorate in physics, but that wasn't why she'd done it. She'd done it because uranium ore was more radioactive than uranium, and she needed to know why. The answer to that question would split the atom, reveal the age of the Earth, and show that matter itself was not eternal, but slowly, inexorably transforming into energy. The thesis defence marked the end of one phase and the beginning of another. Marie and Pierre's work on radioactivity was about to bring them fame, honour, and recognition they'd never sought. But recognition, as they would discover, came with its own set of complications. In November 1903, the Royal Swedish Academy of Sciences announced that the Nobel Prize in Physics would be awarded to Henri Becquerel, Pierre Curie, and Marie Curie for their work on radioactivity. It was unprecedented. The Nobel Prizes had only been established in 1901, and no woman had ever won one. But there was a problem. The initial nomination submitted to the Swedish Academy had mentioned only Becquerel and Pierre. Marie's name was absent. The omission wasn't malicious, merely conventional. Pierre was the established professor. Marie was his wife and collaborator. In the academic culture of 1903, crediting the male half of a husband-wife team seemed natural. Pierre was furious. He wrote to the Academy making it clear that if Marie wasn't included, he would refuse the prize. The work was joint. The discoveries were hers as much as his. Without her insight, her determination, and her 8 years of brutal physical labour, there would be no radium, no Nobel Prize, nothing. The Academy reconsidered. Marie's name was added. The citation acknowledged her role in the discovery and isolation of radium and polonium. Pierre had forced the issue, and the Academy had bent. It was a small victory for recognition, but it set a precedent. Marie became the first woman to win a Nobel Prize. They didn't attend the ceremony in Stockholm. Pierre was too ill, and they couldn't afford the trip. The money that came with the prize, 70,000 Swedish krona split 3 ways, was welcome, but not life-changing. They used it to install a modern bathroom in their house, and to help struggling students and family members. They didn't patent their radium extraction process. Other scientists had asked them to, pointing out they could become wealthy. Pierre refused. Science belonged to everyone. Discoveries were not commodities to be hoarded. They published their methods in full detail so anyone could replicate them. The Nobel Prize changed everything anyway. Suddenly the Curies were celebrities. Journalists appeared at their door, wanting interviews and photographs. Society hostesses sent invitations to dinners and salons. The French Academy of Sciences, which had rejected Pierre's membership application twice before, now welcomed him. The University of Paris finally created a proper professorship for him, along with a laboratory and funding for 3 assistants. One of those positions went to Marie, making her the first woman in France to hold an official teaching position at the Sorbonne. But the attention was exhausting. Marie hated it. She'd never sought fame. She wanted to work, to understand radioactivity, to push deeper into the mystery. Instead, she spent her days responding to correspondence, posing for photographers, and attending ceremonies. Pierre felt the same. His health continued to deteriorate. The pains in his joints worsened. He developed a persistent cough. His hands shook so badly he could barely write. Neither of them understood that the radium they handled daily was destroying their bodies cell by cell. Radium's danger wasn't yet known. It glowed. It emitted heat continuously, without any apparent source of energy. It could expose photographic plates through layers of paper. It could make the air around it conduct electricity. These were fascinating properties, not warnings. Pierre carried test tubes of radium salts in his vest pocket to show colleagues. Marie kept samples on her desk because she found the glow beautiful in the dark. They had no idea. By 1904, the scientific community was beginning to understand that radioactivity represented something fundamentally new. Ernest Rutherford in Canada had shown that radioactive elements transmuted into other elements over time. Uranium decayed into thorium, thorium into radium, radium into an inert gas he called emanation, later known as radon. This was alchemy, but real. Elements weren't eternal, they changed. The atom itself, long thought to be indivisible, was revealing an internal structure. Pierre became obsessed with understanding radium's heat production. The element continuously emitted energy, about 100 calories per gram per hour, enough to melt its own weight in ice every hour forever. Where was this energy coming from? It violated the law of conservation of energy unless something inside the atom was being consumed. Pierre and Marie measured the heat output precisely, confirming that it never diminished. This tiny sample of radium would continue producing heat for thousands of years. The implications were staggering. If radioactive elements released energy continuously over vast timescales, then the Earth itself might be heated from within by radioactive decay. Geologists had calculated that if the Earth were cooling from an initially molten state, it couldn't be more than 20 or 30 million years old. But biologists and paleontologists insisted that evolution required hundreds of millions of years. Radioactivity might resolve the contradiction. The Earth could be ancient beyond previous imagination, kept warm by radioactive decay in its interior. In 1904, Marie gave birth to their second daughter, Eve. The pregnancy was difficult. Marie was weakened by years of exposure to radiation, though she didn't know it. Eve was healthy, but Marie's recovery was slow. She pushed herself back to work anyway. The laboratory now had better equipment, more space and assistants to handle the tedious work. Marie could focus on precise measurements and theoretical questions. Pierre was increasingly unwell. The joint pain was now constant. He couldn't sleep. He fell into depressions that alarmed Marie. Doctors couldn't identify what was wrong. They prescribed rest, which Pierre ignored. He continued working, continued handling radium, continued giving lectures where he demonstrated the element's properties by showing how it glowed in the dark. In April 1906, Pierre attended a scientific meeting in Paris. It was raining. He walked through the streets distracted, thinking about an experiment. He stepped behind a horse-drawn wagon to cross the Rue Dauphine. He didn't see the heavy carriage coming from the other direction. The driver couldn't stop. The horse collided with Pierre, knocking him down. The rear wheel of the wagon passed over his head. He died instantly. He was 46 years old. Marie received the news at home. She was 38. Her partner, collaborator, and closest friend was gone. She didn't cry, not then. She stood very still. Later, she would write in her journal that she couldn't accept it, couldn't believe that Pierre was suddenly absent from the world. She'd lost her mother at 10, her sister at 14, and now her husband at 38. She retreated into silence. The funeral was small. Marie refused a state ceremony. Pierre was buried in the family plot at Sceaux. Marie stood at the graveside holding Irene and Eve, her face blank. Afterwards, she returned home and began writing in a diary addressed to Pierre, as if he could still hear her. The entries record her grief, her inability to function, her sense that life had become meaningless. But there were decisions to make. The University of Paris offered Marie Pierre's professorship. It was unprecedented. No woman had ever held a professorial chair at the Sorbonne. Some faculty members objected. Women weren't suited for such positions. They lacked the necessary authority, the intellectual stamina. Marie accepted anyway. She needed to work. Work was the only thing that might keep her from collapsing entirely. Her first lecture took place in November 1906. The lecture hall was packed with students, colleagues, and journalists who'd come to witness the spectacle of a woman teaching physics at the Sorbonne. Marie walked to the lectern carrying her notes. She began speaking exactly where Pierre's last lecture had ended, picking up mid-sentence as if the interval had never occurred. She lectured on radioactivity, on the properties of radium, on the ongoing research. Her voice was steady. She didn't acknowledge the crowd or the historic nature of the moment. She simply taught. Over the following years, Marie rebuilt her life around work. She supervised doctoral students, expanded the laboratory, and pushed deeper into the study of radioactive elements. She standardized the measurement of radioactivity, establishing the Curie as a unit equal to the radioactivity of 1 gram of radium. She developed techniques for producing radium in larger quantities. She trained a generation of researchers in the new science. But she was lonely. Her closest collaborator was gone. She had colleagues, students, and assistants, but no intellectual equal. She corresponded with other scientists. Rutherford in England, Frederick Soddy, Otto Hahn. They respected her work, but she was isolated in a way that male scientists weren't. She couldn't easily attend conferences where the real exchanges happened in hotel lobbies and over late dinners. Women weren't invited to those gatherings. In 1910, Marie published a massive treatise titled Treatise on Radioactivity. It was over 900 pages summarizing everything known about radioactive elements, their properties, their transformations, and their effects. It became the standard reference work in the field. Anyone studying radioactivity for the next 2 decades would read Marie's treatise. She also decided to apply for membership in the French Academy of Sciences. It would be the first time a woman sought admission to that prestigious body. The campaign was bitter. Traditionalists argued that women were constitutionally unfit for scientific work. Others claimed that admitting one woman would open the floodgates. The Academy took a vote. Marie lost by 2 votes. The rejection was widely publicized. She never applied again. But international recognition continued. In 1911, she won her second Nobel Prize, this time in chemistry, for her discovery and isolation of pure radium. She became the first person ever to win Nobel Prizes in 2 different sciences. This time, she attended the ceremony in Stockholm, bringing Irene and Eve. She gave a lecture describing the years of work that had led to radium's isolation. She was 43 years old. The second Nobel should have been a triumph. Instead, it coincided with scandal. Marie had developed a close relationship with Paul Langevin, a former student of Pierre's and a brilliant physicist in his own right. Langevin was married, unhappily. He and Marie had become confidants, then something more. Letters were stolen from Langevin's apartment and leaked to the press. The newspapers erupted, a widow carrying on with a married man. The hypocrisy was staggering. Male scientists routinely had affairs with no damage to their reputations, but Marie was a woman, and she was held to a different standard. The scandal was vicious. Crowds gathered outside her house shouting insults. Journalists published her private letters. Colleagues who'd praised her work now distanced themselves. Some suggested she should return to Poland. The Swedish Academy, embarrassed, considered asking her to decline the Nobel Prize. She refused. She'd earned it through work, not public approval. She travelled to Stockholm, collected her prize, and delivered her lecture. Then she collapsed. The years of overwork, radiation exposure, and emotional strain had finally broken her health. She spent months recovering in a sanatorium, her kidneys damaged, her body weak. She was 44 and looked 60, yet she returned to work. The laboratory continued. The research expanded. And when war came in 1914, Marie found a new purpose that would save hundreds of thousands of lives. But that transformation from scientist to war hero required her to leave the laboratory and enter a world of military bureaucracy, field hospitals, and the trenches where young men were dying because doctors couldn't see the bullets lodged in their bodies. The war arrived in August 1914, and Marie understood immediately that X-rays could save lives. Surgeons operating in field hospitals had no way to locate shrapnel or bullets lodged in wounded soldiers. They probed blindly, causing additional trauma, often leaving fragments behind that would fester and kill. X-ray technology existed, but it was confined to major hospitals in cities. The front lines had nothing. Marie decided to bring X-rays to the war. She converted her laboratory's Renault automobile into a mobile radiological unit. She installed an X-ray machine, a photographic darkroom, and a generator powered by the car's engine. Then she drove it to the front herself. She was 46 years old, famous throughout Europe, and she was heading toward artillery fire with a trunk full of radium tubes and photographic plates. The military authorities were baffled. A woman driving to field hospitals, operating medical equipment? But Marie had connections now. She'd cultivated relationships with government officials precisely for moments like this. She obtained the necessary permissions and set out. The first trip was chaos. The roads were clogged with refugees fleeing the German advance. Artillery shells fell within earshot. Marie set up her equipment in a commandeered building near the front, trained the medical staff to use it, and took the first radiographs of wounded soldiers. Surgeons could suddenly see exactly where bullets had entered, where bones were shattered, where metal fragments nested near vital organs. Operations became faster, more precise. Infection rates dropped. Survival rates climbed. One mobile unit wasn't enough. Marie returned to Paris and organised the production of more. She recruited women to train as radiological technicians. She standardised the equipment, wrote instruction manuals, and established training programs. She personally taught hundreds of women how to operate X-ray machines, develop radiographs, and protect themselves from radiation exposure. She called these mobile units petites curies, little curies. By the war's end, there were 20 of them, along with 200 stationary radiological installations at field hospitals. Marie had created an entire medical infrastructure from scratch. She also brought her teenage daughter Irene into the work. At 17, Irene was already a skilled laboratory assistant. Marie trained her in radiology, then sent her to operate X-ray equipment at field hospitals near the fighting. Irene spent months at the front, often under bombardment, calmly taking radiographs while shells landed nearby. The Curie women were everywhere the wounded gathered. Marie herself logged thousands of miles driving between field hospitals. She slept in military barracks, ate army rations, and worked 20-hour days. She was exposed to radiation constantly, holding cassettes, adjusting equipment, checking exposures. No one understood the cumulative damage yet. She was already carrying a lifetime's dose from her laboratory work, and now she was adding more each day. The physical toll was severe. Her hands were scarred and burned. Her eyesight was failing. She suffered chronic fatigue and kidney problems. But she kept working. Over 1 million radiographs were taken using equipment Marie had built or supervised. The exact number of lives saved is impossible to calculate, but estimates run into the hundreds of thousands. Yet when the war ended in 1918, Marie received no official recognition from the French government. Male scientists who'd contributed far less were decorated. Marie was ignored. She didn't complain publicly. She returned to her laboratory and resumed the work that had been interrupted 4 years earlier. The Radium Institute had been completed just before the war started. It was a modern research facility, purpose-built for radioactivity studies, funded by the University of Paris and the Pasteur Institute. Marie became its director. She now had resources she'd only dreamed of in those early years in the shed. Proper laboratories, trained assistants, modern equipment, adequate funding. She rebuilt her research program. The war had scattered her students and collaborators, but they returned. New ones arrived, drawn by the Radium Institute's reputation. Marie trained an entire generation of radiochemists. Her laboratory became the world centre for radioactivity research. But radium remained scarce and expensive. The gram Marie had isolated before the war was the Institute's only significant supply. To do serious research, they needed more. In America, radium was being produced commercially, but it cost $100,000 per gram. Marie couldn't afford it. Then an American journalist named Marie Maloney visited Paris in 1920. Maloney was the editor of a women's magazine, and she wanted to interview the famous Madame Curie. Marie rarely granted interviews, but Maloney was persistent. They met at the Radium Institute. Melanie was shocked by what she found. Here was the most famous woman scientist in the world, working in a laboratory that lacked basic supplies. Marie explained that American hospitals had more radium than all the French laboratories combined. Research was being hampered by simple scarcity. Melanie returned to America with a mission. She would raise money to buy Marie Curie a gram of radium. She launched a subscription campaign through her magazine. American women sent donations, small amounts mostly, but they accumulated. Within a year, Melanie had raised the $100,000. But there was a condition. Marie would have to come to America to receive it. Melanie understood publicity. An American tour would generate enormous coverage, advance the cause of women in science, and cement Marie's international reputation. Marie hated public appearances, but she agreed. In May 1921, she sailed for New York with her daughters. She was 53 years old and had never been to America. The reception overwhelmed her. Thousands of people crowded the dock when her ship arrived. Photographers swarmed. Reporters shouted questions. Marie, dressed simply in black, looked bewildered by the attention. Over the following weeks, she travelled across America, visiting universities, factories, and hospitals. She gave lectures, attended ceremonies, and met with scientists. Everywhere she went, crowds gathered. Women especially came to see her, bringing their daughters, wanting them to meet someone who proved that women could achieve the highest levels of scientific accomplishment. President Warren Harding presented her with the gram of radium in a ceremony at the White House. It was contained in a lead-lined mahogany box with a golden key. Marie accepted it on behalf of science, specifying that the radium belonged to her laboratory, not to her personally. She wanted it available for research after her death. The tour exhausted her. The constant travel, the public appearances, the need to be perpetually on, drained someone who preferred laboratory solitude. But it accomplished its purpose. When Marie returned to France, she brought not just radium but international connections, funding opportunities, and renewed public interest in her work. The 1920s saw the Radium Institute flourish. Students came from across Europe and America to study under Marie. She supervised dozens of research projects simultaneously, maintaining the same demanding standards she'd always held. Her laboratory produced important work on radioactive isotopes, on radiation's biological effects, on nuclear physics. Irene was now a full research scientist working alongside her mother. She'd married Frédéric Joliot, one of Marie's students, and they were conducting experiments on nuclear reactions. The pattern was repeating. Just as Pierre and Marie had been collaborators, now Irene and Frédéric worked as a team. Marie's health continued to deteriorate. The radiation exposure from decades of work was causing cumulative damage that medicine couldn't repair. She developed cataracts in both eyes, requiring multiple surgeries. Her blood counts were abnormal. She suffered from chronic weakness and frequent infections. Still, she worked. In 1929, Melanie organized another American tour to raise money for additional radium. Marie was 61 and frail, but she made the journey. President Herbert Hoover presented her with a check for $50,000 to purchase more radium. This time, Marie specified that it should go to the Radium Institute in Warsaw, the one she'd helped establish in Poland. Her last years were consumed by the laboratory. She arrived each morning, reviewed research progress, consulted with students, and conducted her own experiments when her failing eyesight allowed. She was present, directing, teaching, pushing the work forward, even as her body betrayed her. By 1934, she was seriously ill. The symptoms were vague at first: fever, weakness, difficulty breathing. Doctors diagnosed tuberculosis, but the treatment didn't work. She continued coming to the laboratory until she physically couldn't. In late June, she was taken to a sanatorium in the French Alps. On July 4, 1934, Marie Curie died. The official cause was aplastic anemia, a condition where the bone marrow stops producing blood cells. It was caused by prolonged radiation exposure. Her blood had been slowly poisoned by the elements she'd spent her life studying. She was 66 years old. She'd worked until the month she died. Her laboratory notebooks from the 1890s are still radioactive. They're stored in lead-lined boxes at France's National Library. Researchers who wish to consult them must sign liability waivers and wear protective equipment. The pages glow faintly in the dark, contaminated by radium residue from Marie's hands. The funeral was simple, as she'd requested. She was buried at Sceaux, next to Pierre. Years later, in 1995, France recognized what should have been obvious from the beginning. Marie and Pierre's remains were transferred to the Pantheon, the mausoleum in Paris reserved for France's greatest citizens. Marie became the first woman honored there on her own merit, not as someone's wife. Irene and Frédéric continued the work. In 1935, the year after Marie's death, they won the Nobel Prize in Chemistry for discovering artificial radioactivity. They'd created radioactive isotopes that didn't exist in nature, extending Marie's work into new territory. Irene died in 1956 from leukemia, also caused by radiation exposure. 2 generations of Curie women killed by the elements they'd discovered. The scientific legacy is staggering. Marie's work opened entire fields of research: nuclear physics, radiochemistry, atomic medicine, all trace their origins to her laboratory in Paris. The concept of radioactivity itself, the understanding that atoms aren't indivisible but can transform into other elements, revolutionized physics and chemistry. The medical applications have saved millions of lives: radiation therapy for cancer, radioactive tracers for diagnosis, sterilization of medical equipment, all emerged from the foundation Marie established. The petites Curies she created during World War I became the model for mobile medical units used in every conflict since. But perhaps the deeper impact was on possibility itself. When Marie Curie won her first Nobel Prize in 1903, women couldn't vote in France. They couldn't open bank accounts without male permission. They couldn't attend most universities. The idea that a woman could not just participate in science but fundamentally advance it was revolutionary. Every barrier she broke made it fractionally easier for the next woman. Every honour she received, however grudgingly given, established precedent. The Academy of Sciences that rejected her in 1911 would admit its first woman member in 1962. Not quickly, but the impossible had become merely difficult. Marie herself was ambivalent about her role as symbol. She wanted to be judged as a scientist, not as a woman scientist. Yet she understood that her visibility mattered. She mentored women students, advocated for their opportunities, and demonstrated through her own work that excellence was genderless. What remains is the work itself, the discoveries, the methods, the institutions she built. The Radium Institute continues as part of the Curie Institute, still conducting cancer research. Her laboratory notebooks, radioactive though they are, preserve the records of how modern physics began. And somewhere in a lead-lined box, a gram of radium glows faintly, the element she isolated through years of brutal labour, the substance that both defined her life and ended it. Marie Curie's story doesn't end with her death. The radioactivity she unleashed into the world continued its work, transforming science in ways even she couldn't have predicted. Within months of her funeral, physicists were racing toward discoveries that would make her work look almost quaint. The atom she'd helped reveal wasn't just breakable, it was a door to something far stranger. In 1932, James Chadwick discovered the neutron. The atomic nucleus wasn't just protons. There was another particle hiding inside, electrically neutral, almost impossible to detect. This changed everything. Atoms weren't held together by simple positive charges. There was a whole nuclear force at work, something fundamentally new in physics. 2 years later, Marie Curie and Frédéric Joliot made their breakthrough. They bombarded aluminum with alpha particles and created a radioactive isotope that didn't exist in nature. Artificial radioactivity. You could make elements do things they'd never done before. The achievement won them the 1935 Nobel Prize, making the Curies the family with more Nobel Prizes than any other in history. But the implications were darker than anyone realized. If you could create new isotopes, if you could transform elements artificially, what else became possible? In 1938, Otto Hahn and Fritz Strassmann in Berlin did an experiment that shouldn't have worked. They bombarded uranium with neutrons, expecting to create heavier elements. Instead, they got barium, an element much lighter than uranium. The uranium nucleus had split in half. Lisa Meitner, a Jewish physicist who'd fled Nazi Germany, worked out what had happened. When the uranium nucleus broke apart, it released energy, enormous energy. Einstein's equation, E equals mc squared, suddenly wasn't theoretical. Matter was converting to energy right there in the laboratory. They called it fission, the splitting of the atom. The timing was catastrophic. This discovery came in 1939, the year World War II began. Within months, physicists across the world understood what it meant. A weapon. A bomb that derived its power not from chemical explosives, but from the nucleus itself. The Manhattan Project began in 1942. America poured resources into building the first atomic bomb. The scientists involved, including many who'd worked with or been inspired by Marie Curie, found themselves creating something unprecedented, a device that could destroy entire cities. They succeeded. On July 16, 1945, in the New Mexico desert, the first atomic bomb detonated. The explosion released energy equivalent to 20,000 tons of TNT. The flash was visible 200 miles away. A mushroom cloud rose 7 miles into the atmosphere. J. Robert Oppenheimer, who led the project, later said he remembered a line from Hindu scripture. "Now I am become death, the destroyer of worlds." 3 weeks later, Hiroshima. 3 days after that, Nagasaki. The bombs killed over 200,000 people, most of them civilians. The world had entered the atomic age, and it had arrived with horror. Marie Curie had been dead 11 years. She'd never know what her discovery of radioactivity would ultimately enable. Whether she would have approved or been devastated, we cannot know. Science doesn't come with moral instructions. It simply reveals what's possible. The Cold War that followed turned atomic weapons into the central fact of global politics. America and the Soviet Union built arsenals capable of destroying human civilization multiple times over. The doctrine of mutually assured destruction kept the peace through the threat of total annihilation. By the 1980s, there were enough nuclear weapons to kill everyone on Earth many times over. Yet the same physics that enabled bombs also enabled power. Nuclear reactors, designed carefully, could generate electricity without burning fossil fuels. France, in particular, embraced this path. By the 1980s, 70% of French electricity came from nuclear power. The country that had once rejected Marie Curie from its Academy of Sciences now ran on the technology she'd made possible. The medical applications expanded as well. Radiation therapy became more precise. Radioactive isotopes helped diagnose diseases long before symptoms appeared. PET scans, which use radioactive tracers to image the body's metabolism, became routine. Cancer, that would once have been a death sentence, became survivable. But accidents revealed the technology's dangers. 3 Mile Island in 1979, Chernobyl in 1986, Fukushima in 2011. Each disaster released radioactive material into the environment, contaminating land for decades. The cleanup from Chernobyl won't be complete for 20,000 years. The exclusion zone around the reactor remains too radioactive for human habitation. The waste problem persists. Nuclear reactors produce spent fuel that remains dangerously radioactive for hundreds of thousands of years. We've created substances that will outlive our civilization, that will still be deadly long after everyone alive today is forgotten. We bury it deep underground and hope future generations remember where we put it. Marie's laboratory notebooks aren't the only things that glow in the dark. Her house in Sioux, her furniture, her cookbooks all remain contaminated. Her belongings are stored in lead-lined containers. The clothes she wore, the pens she used, the dishes she ate from, all carry enough radium to be hazardous. The Radium Institute she founded, now part of the Curie Institute, continues cancer research. The building where she worked is carefully maintained, but certain rooms remain off-limits. The radiation levels are still too high. Her grave at the Pantheon required special preparation. The coffin is lined with lead, nearly an inch thick. Even in death, she's too radioactive to handle normally. When they moved her remains from Sioux to the Pantheon in 1995, workers wore protective suits. The woman who'd once carried radium in her pockets now required hazmat protocols. The scientific method she pioneered, the meticulous measurement and documentation, became standard practice. Modern laboratories follow procedures she helped establish. The careful recording of observations, the systematic testing of hypotheses, the quantitative analysis of results, all trace back to those years in the shed on Rue Le Monde. Her approach to collaboration set patterns too. The way she worked with Pierre, as genuine equals sharing credit and responsibility, established a model. Science done in partnerships, with recognition fairly distributed, replaced the old model of solitary genius. Though implementation remained imperfect, she'd proven it could work. The barriers she broke didn't stay broken. Women still face obstacles in science, still struggle for recognition and funding, still find themselves judged differently than male colleagues. But the existence proof matters. She'd shown it was possible. That counts for something. By the 1960s, women were entering science in growing numbers. Not easily, not equally, but increasingly. Marie Curie's name appeared in textbooks, usually as the lone woman among pages of men. Girls read about her and thought maybe perhaps if she could do it. Rosalind Franklin's work on DNA structure in the 1950s, largely uncredited until after her death, echoed Marie's experience. Jocelyn Bell Burnell's discovery of pulsars in 1967, which earned her male supervisor a Nobel Prize while she got nothing, repeated the pattern. The Academy of Sciences that rejected Marie in 1911 didn't admit its first woman until 1979, and then only grudgingly. Progress, but glacial. The institutions changed slower than the science. Marie's daughters both became scientists, continuing the family tradition. Irene, as we've seen, won her own Nobel Prize. Eve, the younger daughter, became a writer and war correspondent. She wrote her mother's biography in 1937, 3 years after Marie's death. The book became a bestseller, introducing Marie to a wider audience beyond the scientific community. That biography shaped how generations understood Marie Curie. Eve portrayed her mother as dedicated, tireless, indifferent to personal comfort or recognition. A woman driven purely by curiosity and the love of knowledge. It was true mostly. But it was also simplified, scrubbed of complexity and doubt. The real Marie was more interesting than the icon. She had ambitions, yes, and scientific passion, but also stubbornness, pride, and occasional pettiness. She held grudges. She could be cold. She made mistakes and sometimes failed to acknowledge them. The human being was more complicated than the symbol. But symbols matter too. The Marie Curie who appears in textbooks and biographies, the tireless scientist who overcame all obstacles through brilliance and determination, serves a purpose. She makes the impossible seem achievable. Whether that's fair to the real woman who lived that life is another question. The elements she discovered remain in use. Radium, despite its dangers, still finds applications. Americium-241, a descendant of Marie's work, sits inside most smoke detectors. A tiny amount of radioactive material ionizes air, allowing current to flow. When smoke particles interrupt that current, the alarm sounds. Marie's discovery, domesticated, keeping people safe in their homes. Polonium, the first element she isolated, became a tool of assassination. Alexander Litvinenko, a Russian dissident, was poisoned with polonium-210 in London in 2006. It's nearly undetectable, leaves no taste, and delivers a fatal dose in micrograms. The element named for Marie's homeland became a weapon. The gram of radium she isolated, the one that took 4 years and 8 tons of pitchblende, no longer exists as she left it. Radium decays with a half-life of 1600 years. The sample she held has lost perhaps 3% of its radioactivity since she died. In 1600 years, half will be gone. In 3,200 years, only a quarter will remain. Eventually, on timescales long after human civilization has risen and fallen, the radium will decay completely. It will transform through a chain of intermediate elements, each one radioactive, each one unstable, until finally it becomes lead. Stable, inert, safe. The element that poisoned Marie will ultimately become harmless. But that's thousands of years away. For now, the radium glows. The notebooks remain dangerous. The laboratory where she worked still registers on Geiger counters. Her legacy, quite literally, is radioactive. The question she couldn't answer, the one that haunted her final years, remains unresolved. Was it worth it? The knowledge gained, the lives saved, the technology enabled, all balanced against the weapons, the accidents, the deaths from radiation exposure. She gave her life to science. That's not metaphor. The radiation exposure from decades of work with radioactive materials killed her. She knew the risks, understood them better than almost anyone, and chose to continue anyway. The knowledge mattered more than safety. That choice is harder to celebrate now than it was in 1934. We've seen what radioactivity unleashed can do. We've watched mushroom clouds rise over cities. We've buried waste that will remain deadly longer than recorded history. We've created problems that will outlast nations. Marie opened a door that cannot be closed. The knowledge exists now, permanently. We can't unknow how to split atoms or extract energy from nuclei. We can only choose how to use that knowledge, and we've chosen both healing and harm. She would have understood that ambiguity. Science reveals truth without moral content. What we do with truth, the choices we make, the applications we pursue, those determine whether knowledge helps or harms. The atom itself is neutral. We make it into medicine or weapons. The shed where she worked was demolished decades ago. The building that replaced it is gone too. That corner of Paris, where modern physics began, has been rebuilt, redeveloped, made ordinary. No plaque marks the spot. You could walk past it, unknowing, but the wave she started still spreads outward, still shapes the world. Every nuclear power plant, every radiation treatment, every atomic clock, every smoke detector, every medical tracer, all descend from those years in the shed. From the woman who stirred tons of pitchblende in an iron pot. who isolated elements with her own hands, who measured radioactivity with instruments she built herself. She worked in the dark, literally. The shed had poor lighting. She often worked by the glow of radium itself, the eerie green luminescence that she found so beautiful. That glow was killing her slowly, particle by particle, breaking down her cells even as it illuminated her work. The beauty that killed her would outlive her by millennia. But Marie Curie's story doesn't end with radiation poisoning and a lead coffin. It continues through her daughters, through the students she trained, through the institution she built. The ripples spread outward in ways she never anticipated, creating a scientific dynasty that would shape the 20th century. Her daughter Irene inherited more than her mother's intellect. She inherited the laboratory, the mission, and ultimately the same fate. Irene Joliot-Curie was born in 1897, when her mother was still unknown, still grinding pitch blender in the shed. She grew up in a household where radioactivity was dinner conversation, where scientific papers littered the tables, where both parents disappeared for hours into their research. It was not a normal childhood. How could it be? Her mother had won a Nobel Prize when Irene was 6. By the time she was 10, Marie had won a second one. The pressure must have been extraordinary. To be the daughter of the most famous woman scientist in the world, to grow up knowing that everything you did would be measured against impossible standards. Most children of genius crumble under that weight. Irene thrived on it. She studied mathematics and physics at the Sorbonne. During World War I, at 17, she assisted her mother operating mobile X-ray units at the front lines. She saw what radiation could do to help, watching doctors use X-rays to locate shrapnel and bullets in wounded soldiers. She also saw what war could do to human beings, the endless stream of broken bodies that filled the field hospitals. After the war, she returned to Paris and began working at her mother's Radium Institute. She was Marie's assistant, her colleague, eventually her equal. They published papers together. They refined techniques together. They worked side by side in the laboratory where Marie had spent decades. In 1926, Irene married Frédéric Joliot, a physicist who had come to work at the Radium Institute. It was a partnership that echoed Marie and Pierre's, two scientists united by shared passion for research. They combined their names, becoming Joliot-Curie, a hyphenated legacy. And in 1934, the year Marie died, Irene and Frédéric made a discovery that would earn them their own Nobel Prize. They had been bombarding aluminum with alpha particles, the same kind of radiation that Marie had studied for decades. But they noticed something strange. After they stopped the bombardment, the aluminum continued to emit radiation. It shouldn't have done that. Natural radioactivity comes from naturally radioactive elements. Aluminum isn't radioactive. What was happening? They had created artificial radioactivity. By bombarding stable aluminum with alpha particles, they had transformed it into a radioactive isotope of phosphorus. They had made a new element, one that didn't exist in nature, one that existed only because they had created it in the laboratory. This was enormous. Marie had discovered natural radioactivity, the property of certain elements to spontaneously emit radiation. Irene had discovered that you could make any element radioactive if you bombarded it with the right particles. You could create radioactive isotopes on demand. The implications were immediate and far-reaching. Radioactive isotopes could be used as tracers in chemistry and biology. You could track where specific atoms went, in chemical reactions, in biological processes, in living organisms. You could label molecules and follow them through metabolic pathways. You could inject radioactive compounds into patients and watch where they accumulated, diagnosing diseases that were invisible to X-rays. Modern nuclear medicine stems from this discovery. Every PET scan, every radioactive tracer used in diagnosis, every targeted radiation treatment, all descend from what Irene and Frédéric figured out in 1934. They won the Nobel Prize in Chemistry in 1935 1 year after Marie's death. Irene was 38, the same age her mother had been when she won her first Nobel. The symmetry is almost painful. Mother and daughter, both Nobel laureates, both working with radioactivity, both dying from it. Because Irene Joliot-Curie died of leukemia in 1956 at 58. The same disease that killed her mother, caused by the same exposure to radiation, accumulated over decades of work with radioactive materials. She knew the risks. She had watched her mother die. She continued anyway. Her husband Frederick survived her by 2 years, dying in 1958 of liver disease, likely caused by radiation exposure. They had worked together for 30 years, discovered artificial radioactivity together, won the Nobel Prize together, and died together from the work they loved. The pattern is almost too neat to be real, but it is real. Marie and Pierre, dead from radiation. Irene and Frederick, dead from radiation. 2 generations of scientific partnership. 2 Nobel Prizes, 4 dead scientists. The price of knowledge written in bone marrow and blood cells. Marie's younger daughter Eve took a different path. She became a writer and pianist, deliberately choosing a life away from science, away from the laboratory, away from the radiation that had killed her parents and would kill her sister. She lived to 92, dying in 2007, the last surviving link to Marie Curie's household. She wrote her mother's biography, the definitive account of Marie's life, published in 1937. It's the source for much of what we know about Marie's inner thoughts, her struggles, her motivations. Eve watched everyone else in her family die from science. She was the only one who escaped. The Radium Institute that Marie founded continues today as the Curie Institute, one of the world's leading cancer research centres. The irony is thick enough to taste. The element that Marie discovered, the radiation that killed her, now saves lives. The institute she built to study radioactivity now uses that knowledge to fight cancer. Her death funds research into preventing other deaths like hers. Thousands of people are alive today because of treatments developed at the Curie Institute. They owe their lives indirectly to a woman who died from the very thing that now saves them. That's the ambiguity again, the dual nature of radioactivity. It kills and it heals, depending on how it's used, how it's directed, how it's controlled. Marie's laboratory notebooks remain in the archives in Paris, stored in lead-lined boxes. Researchers who want to consult them must sign a waiver acknowledging the radiation risk and wear protective equipment. The pages are still dangerous, will remain dangerous for centuries. Her cookbook, the one she used at home, also radioactive. Her furniture, her clothes, her personal effects, all contaminated. Everything she touched became radioactive through contact. She carried it with her in her pockets, on her hands, in her hair. The house in Sceaux, where she lived with Pierre, where they raised their daughters, where Pierre returned from the patent office that rainy night in 1906, still stands. It's a museum now. You can visit if you want. You can see the garden where Marie walked, trying to make sense of her grief. You can see the rooms where Irene and Eve grew up. You can imagine the conversations that must have happened there, the debates about science and politics and the future. But you cannot see the shed. That's long gone, demolished decades ago. The site where modern physics began is just a street corner now. Ordinary, unmarked. The building that replaced it has itself been replaced. Nothing remains of the physical space where Marie and Pierre discovered radium and polonium, except the knowledge. That remains. That's permanent. And the radiation. That remains too. If you brought a Geiger counter to the Curie Institute, to the archives where the notebooks are stored, to the museum in Sceaux, it would click, softly, persistently, measuring particles that continue to emerge from atoms that Marie handled a century ago. The half-life of radium is 1600 years. We're only 90 years past her death. The radiation she unleashed is barely diminished. Her grave at the Pantheon, that honour from the French Republic, came in 1995, 61 years after her death. The French government finally decided that she deserved to be buried among the nation's heroes. She was the first woman to receive that honour on her own merits, not as someone's wife. They moved her remains from Sceaux, transported them in a ceremony that acknowledged both her scientific achievements and her significance as a woman who had broken every barrier that stood in her way. The lead coffin was still necessary. Even in death, she remains dangerous. President François Mitterrand gave the eulogy. He spoke of her contributions to science, her 2 Nobel Prizes, her role as a pioneer for women in physics. He did not mention that France had treated her terribly during her life, that the scandal over Paul Langevin had nearly destroyed her, that the French Academy of Sciences had rejected her twice, that she had been more celebrated abroad than in her own adopted country. History has a way of cleaning up its mistakes, of pretending that honour was always given when it was actually withheld until long after it mattered. The ceremony was elaborate, dignified, appropriate for one of the greatest scientists who ever lived. But it happened 6 decades too late. She couldn't see it. She couldn't know that she would eventually be recognised, that her name would be given to schools and streets and research institutes, that she would become an icon, a symbol, a person whose image adorns currency and postage stamps. She died thinking she was controversial, thinking her reputation was damaged beyond repair, thinking history might remember her as much for the scandal as for the science. She was wrong about that. History forgot the scandal. It remembers the science. But it took time. It took decades. It took waiting until everyone who remembered the gossip was dead. Only then could she become the pure symbol of scientific achievement. The woman who overcame poverty and sexism and tragedy to discover fundamental truths about nature. The real Marie was more complicated. She was brilliant but difficult. She was dedicated but stubborn. She was pioneering but also privileged in ways she didn't always acknowledge. She had opportunities that other women didn't, connections that opened doors, a husband who supported her work at a time when most women's husbands forbade them from working at all. She succeeded partly because she was extraordinary and partly because circumstances aligned in her favour. Both things can be true. Her genius was real. Her advantages were also real. Neither fact diminishes the other. What's undeniable is the cost. She paid with her life. So did Pierre. So did Irene. So did Frederick. 4 scientists, 2 generations, all dead from radiation exposure. The price of knowledge measured in destroyed bone marrow and cancerous cells. Was it worth it? That question has no answer. Or rather, it has too many answers depending on who's asking and when and why. For Marie, it was worth it. She chose this path knowing the risks. She could have stopped after Pierre died. She could have remarried, retired, lived a comfortable life as a famous widow. She chose instead to continue the work, to push deeper into radioactivity, to accept the damage it was doing to her body because the knowledge mattered more. For the soldiers treated with X-rays during World War I, it was worth it. For the cancer patients treated with radiation therapy, it was worth it. For the millions of people whose lives have been saved by nuclear medicine, it was worth it. For the scientists who died early deaths from radiation poisoning, perhaps they would have chosen differently had they known. We cannot ask them. The question of worth assumes we can separate benefit from cost, as if they exist on different ledgers. But Marie Curie's life demonstrates that they're the same thing. The discovery was the cost was the discovery. You cannot have one without the other. She opened a door into the atom itself, into the fundamental nature of matter and energy. Behind that door lay power beyond anything humanity had wielded before. Nuclear medicine, nuclear energy, nuclear weapons. All of it traced back to the work done in that shed on Rue Lomond, to the woman stirring vast cauldrons of pitchblende, to the blue glow in the darkness that she thought was B. Awful. She couldn't have known where it would lead. How could she? She was investigating a curiosity, a phenomenon no one understood. She was measuring, calculating, isolating, purifying. She was doing science. The applications came later, developed by others who built on her foundation. But the foundation was hers, and the cost of laying it was her life. The radium that killed her is still killing. Her papers from the 1890s are kept in lead-lined boxes at the Bibliothèque Nationale in France. They will remain radioactive for another 1,500 years. Anyone who wishes to examine them must sign a liability waiver and wear protective equipment. The notebooks where she recorded her experiments, the cookbooks she used in her kitchen, even her furniture, all contaminated. Her body was laced in a lead-lined coffin. Her daughter's body too. The radiation they absorbed continues to emit particles, continues to decay, continues to seek equilibrium with the universe. Energy cannot be destroyed, only transformed. The energy that Marie Curie released from the atom became part of her, and part of her remains in that energy, still, cycling through the cosmos. There's poetry in that if you can look past the tragedy, but the tragedy is real. 34 years old when she won her first Nobel Prize, the youngest woman ever to receive it. 44 when she won her second. Dead at 66, her body destroyed by the substance she discovered. 32 years of declining health, of increasing pain, of watching her hands shake and her vision blur and her bones weaken. 32 years of knowing what was happening and continuing anyway. The question we should ask is not whether it was worth it. The question is, what kind of person chooses this path? What internal calculation allows someone to continue work that's killing them because the work matters more than the living? Marie Curie was not a martyr. She did not seek suffering. She took precautions when she understood the danger, though those precautions were inadequate. She simply valued discovery above safety. She believed that understanding nature was worth personal risk. That belief shaped the modern world, but it also destroyed her. Both facts are true. Neither cancels the other. We live now in a world transformed by her work. Radiation therapy treats millions of cancer patients every year. Medical imaging use sign G radioactive tracers diagnoses diseases that would otherwise go undetected. Nuclear power plants generate electricity for entire nations. Smoke detectors in ordinary homes contain radioactive elements. The technology is everywhere, woven into modern life, so thoroughly that we forget it exists. None of this would be possible without Marie Curie's work, and yet the same knowledge that saves lives also threatens them. Nuclear weapons exist because we understand radioactivity. The bombs dropped on Hiroshima and Nagasaki killed hundreds of thousands. The Cold War arms race brought humanity to the brink of annihilation. Nuclear accidents at Chernobyl and Fukushima contaminated vast regions and displaced hundreds of thousands. The knowledge is neutral, the applications are not. Marie Curie disco veered something fundamental about nature. What humanity chose to do with that knowledge is humanity's responsibility, not hers. She cannot be blamed for the bombs any more than she can be credited with every life saved by radiation therapy. She opened the door. Others walked through it. But here's what's remarkable. She knew the door led somewhere dangerous. She saw what radiation did to living tissue. She watched her husband suffer. She felt her own health declining. And still she continued, not out of recklessness, but out of conviction. The knowledge mattered. Understanding mattered. Truth mattered more than safety. That conviction is rare. Most people, faced with a choice between comfort and discovery, between safety and truth, choose comfort, choose safety. Marie Curie chose differently. Teli again and again, for decades. The cost was her life. The reward was knowledge that changed everything. Whether that trade was worthwhile depends entirely on what you value. If you value individual, human life above all else, then no discovery is worth dying for. If you value knowledge and progress, then perhaps some discoveries are worth any cost. Marie Curie made her choice. She chose knowledge. She chose work. She chose discovery, even when it was killing her. We inherit the consequences of that choice. We live in the world her work created, a world with radiation therapy and nuclear power and atomic weapons, a world where matter and energy are understood to be interchangeable, a world where the atom has been split and harnessed and weaponized. She could not have predicted all of this. She was investigating a phenomenon, following evidence, doing science, but the path she opened led here to our present moment, where her legacy is both miraculous and terrifying. The woman who died from radiation exposure made possible both cancer treatment and nuclear war. Both futures were latent in her discovery. Both potentials existed in the radioactive elements she isolated. The duality is fundamental. You cannot have the medicine without the weapons. You cannot have the power without the danger. The knowledge exists now, released into the world, and it cannot be recalled. Marie Curie's story is ultimately about the cost of knowledge. Not just the personal cost, though that was immense, the broader cost, the cost to humanity of understanding forces we cannot fully control. She gave us power over the atom. That power has saved millions of lives. That power has threatened to end civilization. Both statements are true. The knowledge is permanent. The consequences continue to unfold. And somewhere in a lead-lined coffin in the Pantheon, the woman who started it all rests, still radioactive, still dangerous, still glowing faintly in the darkness. The blue light that fascinated her, that she thought was beautiful, that she carried in her pocket to show friends, the light that killed her, it's still there. It will be there for another 1,500 years, long after everyone who remembers her name is dead, long after the buildings she worked in have crumbled, long after the history books have been rewritten 1,000 times. The radium endures. Energy cannot be destroyed. It transforms, shifts, decays, but it persists. Marie Curie discovered that principle. She proved it with her life. The energy she released from the atom became part of her body, and when her body died, that energy remained, cycling through the universe, seeking equilibrium, never quite reaching it. There's something fitting in that. The woman who unlocked the atom's power became, in the end, atomic herself, indivisible, irreducible, still radiating energy decades after death, still dangerous to approach too closely, still glowing in the dark. She wanted to understand nature. She did. She wanted to contribute to human knowledge. She did. She wanted to be remembered for her work, not for her personal life. That took longer, but it happened. History cleaned up its mistakes. The scandal dead. The gossip was forgotten. The science remained. 2 Nobel Prizes, 2 new elements, a new understanding of matter and energy, a legacy measured in lives saved and lives destroyed, a name that will be remembered as long as humans remember science. She paid for it with everything, her health, her happiness, her life. Whether it was worth it is not a question she would have understood. The work was the point. The discovery was the reward. The cost was irrelevant. She was a scientist. She found truth. Nothing else mattered. And now we know what she learned. We carry that knowledge forward. We use it to heal and to harm. We build with it and destroy with it. We cannot unknow it. We cannot return to a world before radioactivity was understood. The door is open. We must walk through it. Marie Curie walked through first. She paid the price of admission. We inherit both the knowledge and the responsibility. Her story ended in the Pantheon. Ours continues. The radiation continues. The work continues. The consequences unfold. The blue glow persists, and the question remains, Not whether it was worth it, but what we will do with what she gave us. That answer is still being written. So what do we do with a legacy this complicated? Marie Curie didn't discover radioactivity to save lives or build weapons. She discovered it because uranium ore was more radioactive than uranium, and that made no sense. She spent 4 years stirring boiling vats of pitchblende because she needed an answer. The answer killed her. But here's what's true. Every cancer patient who survives radiation therapy owes something to those 4 years. Every person whose smoke detector saves them from fire owes something to that shed on Rue Le Monde. Every doctor who uses a radioactive tracer to diagnose disease owes something to a woman who thought the blue glow was beautiful. And every person who lives in fear of nuclear weapons owes something to the same discovery. Every community displaced by Chernobyl, every victim of Hiroshima and Nagasaki. The knowledge that heals is the knowledge that destroys. You cannot separate them. They're the same thing. Marie made a choice that most of us will never face. She chose understanding over safety. She chose work over health. She chose discovery, knowing it was killing her. Not because she was suicidal or reckless, because the work mattered more. We're still living in the world that choice created. Every nuclear power plant generating electricity, every medical imaging center diagnosing disease, every atomic clock keeping perfect time, every particle accelerator probing the structure of matter. All of it traces back to a woman in a drafty shed who processed tons of ore with her bare hands. She died in 1934. Her notebooks are still radioactive. Her body required a lead-lined coffin. The radiation she unleashed continues, particle by particle, decaying towards stability. It won't reach for another 1,500 years. That's not metaphor. That's physics. Energy cannot be destroyed. It transforms. The energy Marie Curie released from the atom is still here, still cycling through the universe, still seeking equilibrium. She's part of it now. The radiation that killed her carries pieces of what she was. Atoms that were once in her body, transformed by the very forces she studied, scattered across the cosmos. There's something almost perfect in that. The scientist who revealed that matter and energy are interchangeable became proof of her own discovery. She wanted to understand nature. She did. She wanted to be judged on her work, not her gender. Eventually she was. She wanted her discoveries to benefit humanity. They have. They've also threatened to end it. Both outcomes were latent in the discovery. Both potentials existed in the radioactive elements she isolated. The duality is fundamental. You cannot have one without the other. The real question isn't whether her work was worth the cost. She answered that question by continuing until it killed her. The real question is what we do with what she gave us, because the knowledge exists now, permanently. We can't unknow how to split atoms. We can't return to a world where radioactivity is mysterious. The door is open. We're through it. We have to decide what we build on the other side. Marie Curie gave us power over the atom. That power has saved millions of lives. That power has threatened civilization. Both statements are true. Neither cancels the other. We inherit that ambiguity. We live with that responsibility. We make choices about how to use knowledge that someone else died to acquire. She worked in the dark, literally. The shed had poor lighting. She often worked by the glow of radium itself. The blue-green luminescence that she found beautiful, that fascinated her, that she carried in her pocket to show friends. The glow that killed her. It's still there, in her notebooks, in her furniture, in her body. The half-life of radium is 1,600 years. We're barely 90 years past her death. The radiation is hardly diminished. 1,500 years from now, when everything we know has been transformed beyond recognition, when our civilization is archaeology, when the languages we speak are dead, Marie Curie's notebooks will still be radioactive, still dangerous, still glowing faintly if you turn off the lights. That's her legacy, not the Nobel Prizes, though they matter. Not the barriers she broke, though they matter too. Her legacy is the knowledge itself, permanent, dangerous, transformative, still unfolding. She opened a door into the nature of reality. Behind it lay power beyond anything humanity had wielded before. We're still figuring out what to do with it, still making mistakes, still learning. She gave us the tools. What we build with them is our responsibility, not hers. But she showed us something else too, something harder to quantify, but just as important. She showed us that barriers are made to be broken, that poverty and gender and nationality are not destiny, that a girl from occupied Poland with no money and no formal opportunities could become the most celebrated scientist of her age. Not easily, not without cost, but possible. Every woman who enters science walks a path Marie Curie helped clear. Every person who pursues knowledge despite obstacles stands on foundations she helped lay. The barriers still exist. They're lower than they were. That's because of choices she made. She chose to study physics when women weren't allowed in universities. She chose to continue research after Pierre died when everyone expected her to retire. She chose to defend her work when the Academy of Sciences rejected her. She chose to keep working when radiation was destroying her body. Every choice was difficult. Every choice had costs. She made them anyway, because the work mattered. The understanding mattered. The truth mattered more than comfort or safety or approval. That conviction shaped everything. It's why she succeeded. It's why she died. It's why we remember her. The woman who never left occupied Poland as a girl became a citizen of France who was honoured in the Pantheon. The woman who couldn't attend university became a professor at the Sorbonne. The woman who was rejected by the Academy of Sciences won 2 Nobel Prizes. She did it by working harder than anyone thought possible, by refusing to accept no for an answer, by valuing knowledge above everything else, including her own life. Was it worth it? She thought so. That's the only answer that matters. We inherit the consequences, the knowledge she died to acquire, the power she unleashed, the responsibility she passed to us. We're still learning how to carry it, still making mistakes, still trying to use radioactivity to heal rather than harm, still working to ensure that the door she opened leads somewhere worth going. The radiation continues. The work continues. The consequences unfold. And somewhere in the Pantheon, in a lead-lined coffin, Marie Curie rests. Still radioactive, still dangerous, still glowing in the dark. The woman who unlocked the atom's secrets became atomic herself. Indivisible, irreducible, permanent. Energy cannot be destroyed, only transformed. She proved it with her life. She proved it with her death. The energy remains. Cycling through the universe, seeking equilibrium it will never quite reach. Just like the questions she answered and the questions she raised. Just like the power she gave us and the responsibility that comes with it. Just like her legacy itself, dangerous and beautiful, harmful and healing, killing and saving. All of it true, all of it permanent, all of it still unfolding. Marie Curie discovered radioactivity. It killed her. It changed everything. That's the story. Complete, complicated, impossible to simplify. She opened the door. We walked through it. We're still figuring out what's on the other side. The blue glow persists. The radiation continues. The work goes on. And the woman who started it all, the girl from Warsaw who became the most famous scientist in the world, rests in Paris, honoured at last, still glowing faintly in the darkness, still teaching us, still challenging us, still asking the hardest question, not whether discovery is worth dying for, but whether we're brave enough to seek truth even when it costs everything. She answered yes, every day for 30 years. Until it killed her, we carry that answer forward. We build on foundations she laid. We use knowledge she died to acquire. That's the inheritance. That's the responsibility. That's what it means to live in a world Marie Curie helped create. The atom is split, the knowledge exists, the door is open. What we do next is up to us.